Welcome. Couple of notes. We have some administrative notes to make before we get started here. In fact, I'm going to give myself even more room. I bumped the due dates for 1.4, the 1.4 assignment and the 1.5 assignments. They're due on Tuesday, the 28th. So you have lots more time. And I posted the solutions. I'm really making you work for it. I was doing my solutions. Another one, do this again. That's how it should feel, I think, right? If you practice enough, then eventually it gets boring. And that's okay. A couple of notes. I hadn't even got there, but then someone emailed and said, what are we supposed to do? Because some of these are relying on the odd exercises. And so for 1.4 specifically, you're going to do 11 and 12 as kind of a group, 15 and 16 as a group, and then 19 and 20 as a group. And then I've done the solutions for 13 and 14 and 17 and 18, which are kind of the similar duos to what I'm getting you to do. Okay, so I like to pick I try to pick the solutions that that I do, and then you do a follow-up one that's very similar, right? So you have something to work back from. Okay. And so here, can I get it might screenshot loud. Not too loud, okay. Who can, I don't know how to control that, so there's really no way of knowing. But I'll bring that in here, think. So here is my first note. And then my second note is that I changed the due dates because we didn't quite, give you a bit more time, yeah.
It's okay if you did that, the work on a different page.
Yeah.
Because why did I do 11 on a different page and I just brought over the answer and did 12 myself?
Oh, totally, yeah, that's fine, yeah,
Okay.
yeah. If you've already submitted it, you could try resubmitting with, if you have, I guess it just relies on 11. So I don't really need to see 11, but nice to, if you're just starting it, then you get to do all of it.
So in the future, you want to do that.
Yeah, that's good. Yeah.
So those are numbers for the 1.4 and the 1.5.
So you're going to do all the even exercises, but some of those even exercises in 1.4 relied on some odd exercises. So then I did a regrouping of them.
But then what about 1.5?
1.5 is good to go.
So just even ones for 1.5.
Yeah.
Okay, cool.
And so what I did, just to show you, because it might make more sense. So you're going to do all the even ones in 1.4, but then when you get to 11 and 12, 12 refers to 11. And so we did a similar question in class. And so that's why I'm kind of letting you fly on your own. Okay, sort of. And then I did 13 and 14 in the solution, so you can have a look at those. And then a follow-up, kind of a similar question for you to do is 15, 16. All right. Hey, 15, 16. And then I did 17, 18, and then you'll do 19, 20. And then also 22, of course, back to the evens. And then I did 21. Okay. Nice. I do want these as one, ideally PDF. So, and I had a couple of questions about that. So the easiest way to compile a single PDF, there's lots of different ways, right? But you're going to submit your work, submit work as a single, like I said, PDF is probably the easiest, right? And so I like to use just a scanning app. And so You can use a scanning app. I like Genius Scan. Well, actually, I don't like Genius Scan, but I use Genius Scan. Is free. Scannable is really good. And what I did when COVID first hit and we had to figure out, how do we submit things? I just downloaded a bunch of free scanning apps. Has to be free for me. And then I just tested them out, figure out which one you like, right? There might be some features that you like and some that you don't. And so Adobe has a free scanning app. There's lots of different ones. And then I forgot to delete those apps forever. So they're probably still on my phone. But so I use Genius Scan, and you can tell it if you want a single page or multiple pages. So you tell it you want multiple pages, and then you'll be able to upload to your files or save it or email it to yourself or something. However you work in your ecosystem. Right? Okay. Hopefully that makes sense. There are other ways, right? You can Google your way to it. But the PDF takes more or way less space than pictures. And so pictures is going to get kind of unwieldy over time. And so the PDF is going to take a lot less room. So that's nice. Okay. So it has to be, and this is just me being picky. I want you to have the skill of being able to generate a single PDF, right? It's not math, that's just me being picky. Okay. But I force the one upload. Okay. So if you have any questions about that or you want to try it, well, you can try it on your own. But if you have any questions, you can let me know. Okay. Right. What else was there? I know, I paused. Okay, so this weekend I hummed and I hawed and I hummed and I hawed, and I wanted to do matrices. I know, I've already written not covered. And we still can do matrices if you want, but it's a lot of hard work for not that much reward in the end. And so decided to jump straight into chapter 3, which is on linear programming, which is kind of fun. And the extension would be, then we could use matrices later to solve these problems, right? But we don't have to. And so are we okay with not doing matrices? Which means I also had to cut some things like the simplex method for linear programming, relies on matrix algebra, and Markov chains. I know, what a bummer. It's been a long time since I did Markov chains, so I was kind of excited to do it. But we need matrices for that, so. So, and then game theory sounds fun, but it's actually kind of difficult. So we'll see if we get there. Right. I know it sounds so cool and ooh, fancy, but so that's why it's all blank. I couldn't decide, do we keep going with chapter 2 or do we just go to chapter 3? I made a decision. Seems like you guys are okay with it. I'm just going to go straight into chapter 3. Okay. So we've got more applications to finish. That's big. Specifically kind of merchandising problems. But another thing, I was gonna just do it, but these are all kind of subgrouped by chapter, kind of because I imported them. And are you guys okay if I move them into the week blocks where we actually covered them? I think it might make kind of more sense. if I kind of split these up, so don't be alarmed. I'm just gonna move some things around, okay? They'll all still be there, but, okay. Whew, that's a lot of admin. Any questions? Nope. All right. One day, I'll get you guys chatting, maybe. Maybe once it warms up outside, then everyone's all Twitter-pated. Everyone's excited. Stays light out. It's fun to be here. Well, maybe not here, but here. One day.
I have a random question.
Random,
Yeah.
yes.
Okay, so for the exercises, I don't know how that, like, sometimes there's the button that says, mark is done.
Oh, yeah. I don't,
I don't know how that works, but like. sometimes nice to have.
that's just for you.
Okay,
That doesn't do anything for me.
yeah.
Yeah. So, I mean, you can mark it all as done if you wanted
This
to.
doesn't have them now.
Oh, it doesn't have them.
No.
Oh,
I can keep track.
what have I done? Okay, I can
I'm just curious.
I can see. Yeah, usually it's on there. I wasn't even paying attention. But yeah, no, it's not on there. Okay, let me get you some mark as done buttons. Maybe I'll have to like sit down and figure it out though after class. Yeah.
If we're skipping chapter 2 with concepts from it still be on final exam,
No. Oh gosh, no.
dumb question.
No, not well, I mean, scary question. No, only things we cover in class will be on the final exam. Yeah, don't worry. And even though, yeah, so there is another section, we have to have a common final exam, but only 80% common, so, and I know Leslie's not covering matrices anyways, so we're fine. And I would be able to remove that and put something else in instead, so. Don't worry, only things we talk about in class on the final exam. Mark as done buttons. I need to write that down, and I'm gonna do it in kind of a jarring red. This is for me, I'll try to remove it. Double exclamation mark. No wonder you're like, yeah, it doesn't do anything for me, it does something for you.
So before, tests, do you get, practice?
Yeah, I'll give you a practice test. Yeah, sometimes I like to give you a practice for the test, right? So that you can see kind of the breadth of skills that I want you to have, right? But then if you're able to master that, then the test will be a subset. Oh, that's another thing. Since I'm making you work so hard on all these questions, how about a promise that I'm willing to make to you is that all the test questions will be from those chapter questions, not just the ones that you've done. It can be the ones that I've done too. How's that for motivation? What? Well, I mean, you can thank me later. It's a lot of questions that you have to do. But I thought, you know what? I will reserve the right to change numbers, but the type of question will be the same. So instead of 2x plus 3y equals 4, how about 5x plus 4y equals 6 or something, right? But being able to do that type of question. How's that?
No.
Dang it.
It's a lot of questions I have to write on my body.
I know, right? And yeah, you'd have to go to the bathroom and I don't know. In that case, it might be worthwhile just doing the questions. But how's that for kind of reasonable well, in my opinion, reasonable expectations. Also makes it worthwhile doing those problems. Yeah.
We did cheat, right? So- Oh,
Oh.
they're just formulas.
Just formulas. Yeah.
Okay.
Yeah, because we're doing the, okay, yeah. I hadn't really picked a path, but because I'm, yeah, giving you questions that you have potentially seen, I'll give you a formula sheet,
Okay.
right? But I'll give it to you in advance so you know what's gonna be on there. Okay. What are some go-to formulas that you've already been using a lot? Well, y equals mx plus b, that's a good one. I wrote this a ton, y2 minus y1 over x2 minus x1.
Oh, yeah, that's fine.
Y minus y1 is equal to m times x minus x1. Well, in that case, no. There was ax plus by is equal to c. What was the slope of that one? You can do that one on your own. Yeah, you have it. Minus a over b, right? That one I would expect you to get to on your own, right? You solve for y into y equals mx plus b, you'll see it, right? So far, I think that's what we have. Maybe that the cost is the fixed cost plus the variable cost. We played around with that one last day, and we're about to see it tonight on this episode of Math 111. Should call it Math 111. Okay. I can't think of any other ones that we've been using kind of constantly, right? That's probably a good place to start. So far, I promise to have those on your formula sheet. Okay. Or I'll give them to you in the test if you need them, because so far that's not very many. It might be at the front or something, not a separate sheet. Okay. There. Bless you. Who's done economics in here? Well, economics. Lone Ranger. Supply and demand curves. Does that ring a bell? Yeah. Supply and demand curves. I cannot wrap my head around them. I know the math, but the idea is, okay, if I'm a producer and I produce some good, right? So some product, then I will supply as much as the market demands. Okay? And so if we put these on, okay, I need to move these down here. Whoop. So the idea is this. If I have some product, so the number of items, let's say, and if I have the price on the y-axis, usually, now sometimes we swap them, but for now, let's put the price on the y-axis. So if I am on the producer side, then what am I going to want to do as the price increases? I'm going to want to sell more items, right? That's what I want to do. Okay. And so here, this is the supply curve. That's going to be a straight line. Okay. Some y equals mx plus b, right, with a positive slope, right? Now, if I'm the consumer, So now I changed and now I'm buying something. Then as the price is increasing, then the number of items that I want to buy decreases, right? But as the price is decreasing, then the number of items that I want to buy is going to go up. Okay? And so we've got this trade-off. That's supposed to be a straight line. Now, usually we do questions like, oh, if I produce, I don't know, some beverage, and then there's a crop failure, kind of sounds like the Okanagan, right? We produce wine, and then last year our crops all died, our collective crops. And so then, right? What's going to happen to the supply curve? The answer is, I don't know. I don't get that stuff. But I do know the math. What's the math? This is going to be a y equals mx plus b. And this is going to be a y equals mx plus b. And this point here is what we call the equilibrium point. That's where everyone's happy, right? That's where we can kind of all agree that, okay, I'm happy to buy this number of items at this price, and they're happy to supply that number of items at that price, right? And so this is what we call the equilibrium. Which is what? We introduced it last day. It's the intersection of two lines, right? And so is it microeconomics or macroeconomics? It's microeconomics, right? This junk, right? It's too hard for me. The intersection, which is where the blue mx plus b is equal to the green mx plus b. I should have used subscripts on those, right? They don't have the same slope, obviously, right? Because we can see they're not parallel, right? They would have to be parallel if they have the same slope. And they have different intercepts. So just to denote that, how about I ignore it? It's gonna do a little M1, B1, M2, B2. Should we do it? Let's do it. M1, B1, M2, B2. Right, just to indicate that they're different. Right, we can see that the y-intercepts would be different, right? Down here, up here, and the slopes are clearly different as well. Okay, so for us, I'm just going to give you the equations of the supply curve and the demand curve, and then we're going to need to find the equilibrium price. Okay. And so the equilibrium price is when the demand equals the supply. Right? We can all get along, we can all agree that everyone's happy there. Okay. So for us, we're just working with lines, but there's a kind of a large amount of things that we can do with just lines, right? Linear equations. For example, the supply curve for a product is this. So we're told that this is the supply. And the demand curve for the same product is this little guy. Right, both straight lines. We recognize, okay, I just have a y and an x, and then I have a straight line. Right, I can rearrange it. Y equals mx plus b. Question.
Would
Yes. You can use elimination, or I like to, if I have them in terms of y, then I set them equal to each other. And I solve for the x that makes that happen, because that x is going to be this value here.
The two ways, you equal them or stack them.
Yeah. So I'll put that on here. So we can solve by elimination, which we saw last day. Or this is called substitution. Maybe we'll practice both. Just be ready for anything. I always like substitution. And the reason I was setting you up with elimination is because that's what you would need to do matrix algebra. And so that was kind of like a mini version of matrix algebra. And so that's why we spent time doing it. But now we just scrapped matrices. So, womp womp. But I do love matrix algebra. When I was in first year, I hated biology so much. It's like, don't tell anyone. So I did first term of biology because I was first year sciences, first term biology, and I can't do this. Second term, I really don't like it. I don't get it. It's hard and it's not for me. So then I looked through, well, we had the courses were all in a book. And so I'm like studying this book, trying to find a course that I can take. And Math 221, which is linear algebra, you can take it with Calc 2 as a co-requisite. So I did. And then I fell in love with math. So that's what I'm denying you, actually. What if this was the one thing that could spark your love of math? And you can see what I was grappling with all weekend. But I love linear algebra, but it's really hard to teach. I don't know if it's hard to do. Okay, so we've got a supply and a demand curve. Wah, wah. And I didn't take biology in the second term. I haven't since. I know, bad. So I teach math. X is the price. So like I said, sometimes they like to switch it up. And so here, X is the price and Y is the number of items produced. That's opposite of the graph I drew, but they're still going to have the same type of relationship. Okay. Part A, how many items will be supplied at a price of $10? Right. Assuming we have unlimited resources, which we'll tackle in the next chapter, where we don't necessarily have unlimited resources, but assuming we do, then how many items will be supplied at a price of $10? And so X is the price. So I'm going to say let X be 10 in the supply curve. The supply curve is Y equals 3.5X minus 14. All right, make sure you use the right curve, but besides that, nothing to it but to do it. Y is 3.5 times 10 minus 14. It's that minus 14 that's gonna make me work for it. I know, it's so bad. You didn't do biology, did you do math? I did. 35 minus 14, it's 21. Wait. Items. Cool.
I have a question.
Yes.
Because we said Y is price, right?
Oh, yeah, but here, this is where they defined it as, in this scenario, X is the price, which throws me off. But
Okay.
yeah, so you want to read and just follow what they're doing. Right.
Oh, okay, I didn't pay attention to that part.
That's okay. Neither did I initially, and that's why I'm highlighting it. So in this case, nope. X is the price. And Y is the items. Weird. So we can interchange them, but. Okay, how many items will be demanded at a price of $10? And so in B, we're still gonna let X be 10, right? Price is still 10, but now we want to use the demand curve in Y equals negative 2.5X plus 34. So I have Y is negative 2.5 times 10 plus 34. I get 9, but I feel like I fear I made short work of that. Okay, confirmed. 9 items. Remembering that this is the supply, what colors did I use? This is the supply. And this is the demand. At $10, I'm supplying 21 items, but only 9 are being bought. So what am I gonna have to do? Probably lower the price, right, that I can sell these things at. So we want to determine the equilibrium price where everyone's happy. The equilibrium price, and let me just is at the intersection. The intersection. Find myself trying to eavesdrop on the conversation in the hallway. No, the intersection. There. The equilibrium is the intersection of these two lines. So let's jot those down. And we have 2 ways to solve. It doesn't matter how you solve it. Choose your own adventure here. Yeah, I'll show you both. Pick the one that you like and then just stick with it, right? You don't have to learn both, right? Just kind of pick a favorite, learn a favorite, and I'm happy. So 2 ways to solve. The first is by elimination. Where we write these things on top of each other. We try to eliminate one. Let's see here. Y is 3.5x minus 14. I didn't memorize it. And Y is negative 2.5x plus 34. Pick the way you like. Right, you don't need to learn both. Okay. The point of elimination is you add or subtract one of these from the other. I think that we can subtract the lower equation from the top equation, and then I'm gonna be left with 0y, right? Y minus y is 0. Yeah. So y minus y is 0. 3.5x minus negative 2.5x puts me at 6x. Careful with that negative, right? Because if you subtract a negative, then you get a plus. And then we have minus 14, negative 14 minus 34. I don't trust myself. Minus 48. Can solve for x? Yeah.
So, yeah, it's the same as we can equal to each other.
Yeah, we're gonna do both. So we'll start with elimination because I find it's a little bit more difficult, and then by substitution. But as long as you pick one that you like,
So
you don't have to do both.
On a test, would you ask for both ways or just one?
Just one. In fact, I'll just ask you, find the equilibrium price.
That's all.
Yeah.
And then we can decide whatever we want to do.
Yeah, so I want to show you both. And then you can pick a favorite. In fact, maybe I'll bump it over like this. So then we can solve for x here. Solving for x, I move the 48 or the negative 48 over, and I have 48 is equal to 6x. So x must be 48 divided by 6, which is 8. If x is 8, you can use either of these equations. I would recommend using both, right? Checking with both because you should get to the same point, right? If not, then something went wrong, right? And it's not the intersection. And so if y is 3.5x minus 14, then y must be 3.5 times 8 minus 14. Oops. Minus 14. I get 14, but yeah. I'll also check y equals negative 2.5x plus 34. And I really hope that I get y equals 14 again, right? Otherwise I did something wrong. You don't have to double check, right? But you have these two lines, and so you have the ability to, so I encourage it. Negative 2.5 times 8 plus 34. Phew. Y equals 14. So therefore, equilibrium is at x is 8 and y is 14 for this product. Should I do it side by side? Mostly because I want to compare kind of how long it takes in terms of lines, I guess. By elimination or by substitution? Substitution, good. Substitution, right? You've got this this y equals for both of them, right? And you also know that at the intersection, right? those y's have to be the same by definition of the intersection. And so then what you can do is you can say, okay, 3.5x minus 14 is equal to y, which, and just to illustrate, I'll do is equal to the other y, which is equal to negative 2.5x plus 34. But then I kind of remove these guys. Right? If A is equal to B and B is equal to C, then A must be equal to C, right? And so we use that same property. If 3.5x minus 14 is equal to y and y is equal to negative 2.5x plus 34, it just doesn't have that same ring to it, right? But the same property holds. So now I can set them equal to each other. 3.5x minus 14 is negative 2.5x plus 34. Now I can solve for x. How do I solve for x here? I need to collect like terms, right? And so I've got this negative 2.5x that I want to float over here so I don't have to deal with the negatives, right? I'm always keeping an eye out for avoiding negatives if I can, right? And so, but it doesn't matter. But you'll get 3.5x plus 2.5x. And in the same move, I'm going to keep the 34 on the right-hand side, but I'm going to add 14 to the right-hand side, right? Kind of shifting all the non-x's over to one side. So then I have 34 plus 14.
Could you do that same thing with a quadratic formula and then just FOIL? By substitution, like, do you see that?
Let's see here. Do you mean extract these x's?
Like, you would get x2, but like, you would FOIL, but that,
I know I'm so bad at the foils. First, outside, inside, last.
if you're-
Because these are equal to each other. If you were multiplying, yes.
Yeah.
But because they're equal to each other, you just want to float all your like terms together. Nice. Yeah. But if they were multiplied, yeah. I know there's all these kind of terms that I don't know. Like there's feeding the chickens, to feed the chickens when you're distributing. It's the distributive property. What? Although I think feeding the chickens is pretty cute, right? Where you're multiplying into some brackets, right? Now, I was gonna pull a fast one here, but we collect like terms. Why? To unfeed the chickens, basically, right? If I pull out a common multiple of x on the outside here, right? That means that I've kind of extracted an x to the outside and extracted these common x's and I've pulled them outside, right? Then inside I would have 3.5 plus 2.5. But if I just asked you 3.5x plus 2.5x, you would have just added those together, right? But technically what you're doing is you're extracting or you're unfeeding the chickens, taking it all back and pulling out this x, and you're collecting these terms here, right? But you know how to do that, but this is what it looks like mathematically. I don't usually write this step. I would just skip to 3.5 plus 2.5 is, we've already done it, 6. That's nice. And 34 plus 14, is still 48. So I get 6x is equal to 48. Which means that x is 48/6, which we already solved for is 8. Clean that up. I did add a line of work here that I didn't really need to, but they are neck and neck here. And then the rest is the same, right? Because the lines are the same that we're working with. And then this would be the same as before to solve for y. I don't think I need to do that twice, but the equilibrium is at x equals 8 and y equals 14 for this product. Maybe I'll do it in the center. Okay. Good. Equilibrium price. Done. Really just the point of intersection. Any questions about that one? Okay. Consider this scenario. New scenario. You have a business and you make a product and you've got your total cost. We said is your fixed costs plus your variable costs. Your fixed cost, right? That's your rent, your cell phone bills. You have to pay those bills. Doesn't matter if you don't sell anything, you still have to pay up, right? Whereas your variable cost is going to be the per unit cost of production, right? How many man hours does it take? What types of materials does it take? All those things rolled into one, okay? Now, the reason we're doing it all, right, making this product is for what? For the profit. The profit is going to be whatever price you're able to charge. Let's call it capital P. Although usually I use lowercase, but anyways, times however many items you're able to sell. Right? If I asked you, I know it's kind of down here. I didn't move it down far enough. How would you find your break-even point, or how would you define your break-even point? You've got your costs, but you've also got your profit. And I think intuitively we understand what it means to break even, right? That's where your profit finally meets your total costs, right? And so the break-even point, break even is when the total cost equals the profit. Right? You have to cover all your costs before you can actually start bringing in some monies, right? And so that's why you can make a negative profit. A negative profit is still better, right? Especially if you're just kind of starting out or whatever, right? Then you might need to run a negative profit because you still have costs, right? You've still got those fixed costs and you still need to make things to be able to sell them at a loss. Yikes, right? Ideally, you get up to the point where you make more profit than it costs you to run this business, right? And so the break even, just remember you've got this kind of intuitive definition. Okay, well, that's when I actually start making money, right? Up until this, up until we've covered all our total costs, we're bringing in money, but we're not making money. Huh? So the break-even point we only start making a positive profit after the break-even point. I couldn't get away from copying this whole thing, but we have introduced a lot of these already. Oh, revenue. Whoa, what is this? Oh, my P got moved. That's what. Point. There. I called it profit. They've called it revenue. And because I'm too far gone, I'll use red. It's kind of a bad, Emily. They called it revenue. Revenue is profit, right? But it gets confusing with the two P's, right? The price that we're able to charge. Right? So this P is the price the item is sold at. We've seen this before. This is going to have the form B plus MX, or MX plus B if you want. It doesn't matter. All right, so that's going to be a straight line. What's P times X? That's also going to be a straight line, right? With a y-intercept of 0, right? If you produce 0 items, you make 0 monies. Right? Kind of makes sense. Okay, there. Equals the revenue. What are they doing? And also, where are they? Kind of sounds like downstairs, but it can't be upstairs.
It sounds like they're just moving the chairs. Chairs.
I had a morning class last term, and the class next door would just always watch movies, which is really hard to motivate a class to learn math when the other room is just watching a ton of movies. I don't know. Well, I don't know. I could kind of hear it, kind of not. Probably not. 8 a.m. I guess it's a nice way to start your day.
Like, movies are not good.
No, right?
I hate them, and I have to watch like 20 of them this semester. I'm not happy.
Maybe you were in that room. We were so jealous.
Not across the other building.
It was in the E building. I wonder if it was. Okay. So we've got our revenue function, right? The price we're able to sell things at times however many items we sell, right? And then we've got our, oh, I really bungled it, didn't I? I said the profit is the revenue. Well, here it's not. It's the revenue minus the cost. Okay. We only start making, a positive revenue, which is a profit. A positive revenue. In business math, we just call it all profit, and then you can have a negative profit and a positive profit, but it makes more sense to call it revenue, and if it's positive, you get a profit. Fair enough. I'll highlight that so I don't forget. Company makes a profit if the revenue is greater than the cost. You know? And there's a loss if the cost is greater than the revenue. But I think we all would have gotten there on our own. And the point where the revenue equals the cost is called the break-even point. Another intersection of two lines. We know how to do that, right? It's just applying all these concepts, right? And so this is the intersection of the two lines. Got an example here. They use Y, but I replaced it with C just for simplicity because it's the cost. So if the revenue function of a product is 5 times X, right, then the cost of the function or the cost function is 3X plus 12. Now, if we kind of break down C equals 3X plus 12, my fixed costs would be 12. And my variable cost is 3X or 3, depending on how you want to phrase it, right? 3 per unit or 3X. What about, I'll write it over here. The revenue is 5 times X. That means that we're able to sell the item at a price of 5, right? Each item sells at a price of 5. Five units, right? 500, 5,000, 5 million. What? I know. Awesome, right? Got your costs. They would have to be in the same units. Hundreds, thousands, millions. 12 million fixed costs. I think it can happen. Not sure what business. Hey, if 4 items are produced, what will the revenue be? Now we will make the assumption that if you produce it, it will sell, right? And so that's an oversimplification, of course, but I'll clarify here. And sold. We need to figure out what the 4 is. 4 has to be the number of items. And so X must be the number of items, right? There's a cost per item and there's also a revenue per item. And so here we're going to let X be 4. And we want to know what's the revenue. The revenue is going to be 5X. So the revenue is 5 times 4. Revenue is 20 units. Let's see. B, what's the cost of producing 4 items? So again, we're going to let X be 4 and see how they compare. The cost is 3X plus 12. So I get 3 times 4 plus 12. Uh-oh, close. It's going to cost me $24, let's say. And I'm going to make 20. Oh, what if I make one more? Well, I've got an additional $3 cost if I make one more, right? But I have 5 more in revenue, right? And so they're just going to trade off. how many items should be produced to break even? That assumes that you remember what the break even point is, right? But that's where the cost and the revenue are the same, right? The intersection. And so here, to break even. Well, I'm curious. We can do it by elimination, but in this case, I think substitution is going to be a little bit easier, a little bit quicker, just because I say so. I'd have to rewrite them in terms of Y's and things like that. But for the break-even point, if I use the definition that the revenue is equal to the cost, right? Should I put that on your formula sheet? Be nice, wouldn't it? You can remember it. No. No, you have to remember it. Made a decision. It's some theory that I want you to know. Not on your formula sheet. That doesn't exist yet, but also making a note to myself. There. You can remember that. Then I can make it out of 2 marks instead of just 1. That's nice. Because then you have to show me that you remember the break-even point and how to solve for the intersection. So I've got 5 times x is the same as 3x plus 12. Collecting like terms for my x's, right? I'm going to move this 3x over to the left-hand side by subtracting 3x from both sides. And so I get 5x minus 3x is equal to 12. You could pull out that x just to visualize, but we are just working with the coefficients, right? So the things attached to the x's. And so you can take 5 minus 3, and then that's how many x's you're left with. 5x minus 3x is 2x, puts me is equal to 12. So x 6. So at 6 items, I'll break even. Right? How much money am I going to have to fork out in order to make 0 profit? Right? In order to bring home nothing, but also break even, right? I am going to have to, let's see here, the cost is 3x plus 12. And at x equals 6, I get 3 times 6 plus 12. Let's see here, 3 times 6 plus 12. It's going to cost me $30. What should your revenue be? If I'm breaking even, then by definition, the revenue should also be 30, right? Which you can confirm with the revenue is 5 times x, and the revenue is 5 times 6. Revenue is 30. Right? We force them to be equal to each other. So they should be the same. It's always nice to be able to check your work. Okay. Well, we already did D, I guess. Womp womp. What will be the revenue and the cost at the break-even point? I'll just label this D. Ta-da! Did it. After doing this, I was starting to wonder what we could possibly be asked later. Well, it turns out there's nothing. Okay. Any questions about that? Okay. Yeah, I know. I'd feel a little guilty. So how about we just jump into chapter 3? I could do it, but let's save it. We'll save it for a rainy day, right? Yeah, delayed gratification. Yeah. You'll want it in March. Not now. You don't want to waste it now. Okay. Now I wonder. Nope. I really dropped the ball today. I made these. I don't think I posted them, but that's okay. We're gonna just step through them. I've got a lot to say before we start getting into this stuff anyways. Buy myself some time. I'm good at that. Let me add a page. But I did want to, come on. Can you see me struggling? You can. Sometimes it has this, whoa, this nice kind of hidden feature where it just hides stuff. Okay, it's not what I wanted, but. There, I don't give breaks, I guess, mostly because I forget. But there, you had a break. While I do this. Okay. Yeah. Maybe we'll use that. Okay. Chapter 3, linear programming. Sounds fun. It is. It's kind of a nice way to combine the concepts that we've learned so far, right? About lines, right? Linear, it's right there in the name. Y equals mx plus b. Right, that's a straight line. So we know about that already. Programming sounds fancy, right? And it will be. And we're going to use what's called the geometric approach, where we're just going to use graphs. So not matrices, but we could make the extension later on, but we're not going to. Okay. So there's only 2 learning objectives and they read basically the same. And so we don't know what this means yet, but we will. Solve linear programming problems that maximize the objective function, or solve linear programming problems that minimize the objective function. Which means that we're going to have something that we either want to maximize or minimize. Okay. In general, we can call this optimization. Optimization is a huge field in math, computer science, where we're just trying to find maximums and minimums all the time. And UBCO actually has a really strong optimization team. And so that's kind of cool. So we'll get to see a little bit what they do, but we're just maximizing and minimizing, right? If I want maximize something. If I run a business, for example, that's kind of the most tangible thing. Some things I might want to maximize. Profit. Ah, that's a good one. What if I want to maximize, I don't know, I want to maximize my time. We're going to use a lot of profit ones, but maybe I want to maximize my time, right? How do I allocate my time? And
Supply.
oh, nice. All kinds of things. I'm running out of things, so I don't expect you to. But our main one that we want to maximize is profit, of course. Whereas in the next section, we do the same thing, but we want to minimize stuff. So we want to minimize probably cost. I know I took the freebie. Right, we've got some costs. We want to minimize those costs. Kind of confusingly, maybe you want to minimize your time, right? Depends on what you want to, what the end goal is, right? Want to minimize how much of a product you use and still do some other stuff, right? So these things can get kind of tricky, right? Depending on the scenario, right? But usually we want to maximize profit and we want to minimize costs. And usually we want to do those things in tandem, but we're just going to consider them separately. So optimization, nice. How we're going to do it is we're going to have some objective function, okay? Just like it says here. So the objective function is either going to be a function for the profit or a function for the cost, right? And so our objective function is the function we want to optimize. And I'll say optimize, and that can mean either maximize or minimize, depends on the scenario. Like I said, today we'll just see maximization problems, and then next day we'll do minimization problems, but how we tackle them stays the same. So that's nice. So the function we want to optimize, for example, a profit function or a cost function. Okay. We usually have constraints, right? So if I'm looking at a profit function and I want to maximize my profit, right, then you just keep producing, and you make as much money as you want, right? We also saw the demand curve is going to kind of hamper that, but usually we have constraints like there's only so many hours in a week that we could produce things, right? That's a limitation, right? And so a physical limitation on, you know, how many hours it takes to produce one item, right? So that's going to hold you back. Materials, right? Maybe you only have enough materials to make 10 things in a week, right? And so these are all your constraints. So, the constraints are going to be functions that put constraints on our objective function. I know, wishy-washy. Functions that put constraints on the objective function. For example, right, the amount of materials available, oops. Time available, right? It takes time to produce these things. Machines that we have available to us if we're using machines, right? And so the amount of materials available, time available, machines, all these things that are gonna hamper your profits. Bump that, wait, down there. Okay. To solve these problems, all of these guys, these will all be linear functions, right? So they're just going to be straight lines, y equals mx plus b. And so these will be linear equations, y equals mx plus b, with a twist. Usually, if I have a limited number of resources, right, then I have up to and including that y, right? And so we're going to incorporate some inequalities. I know, less than, equal to, greater than or equal to, less than, greater than, those fun ones. So linear equations or inequalities, just as a refresher on inequalities. You have the less than, right? You read it as less than. So if you have A less than B, right? A is less than B. I never got the gator, the alligator eats the bigger one, because I always kind of got turned around and thought, well, am I the alligator? Or I don't know why I couldn't wrap my head around it, but I couldn't. And so I had a student one time tell me, well, you know, that's just an L on its side. And then you can just read it as A is less than B, right? And so the one that makes the L is the less than, and the other one is greater than. Just need to remember one, and then you can remember the other one. So A is less than B. As a little reminder, if I put a line underneath, then it's up to and including that endpoint, right, in the interval, whereas the less than excludes that endpoint. That's not going to be a concern for us for now, but I just want to highlight it while we're doing our little refresher here. So this is less than or equal to. And then we've got greater than. And we've got greater than or equal to. If you want, because I know inequalities can be kind of sticky sometimes, right? If you want to start writing it out in words, you're welcome to, right? You don't have to. I need you to be able to read the inequalities, but I don't need you to be able to write them yet. What you'll find is you'll get so annoyed with having to write it out. You'll be looking for some shorthand, and you have shorthand, right? So that's how you'll start to use it. But if you want to just use words, that's totally fine, right? But eventually, after you've written it so many times, there's got to, oh yeah, there is some shorthand for this. Right? I think in general, that's how you should develop shorthand, right? It's just kind of make you write it out a bunch of times properly, and then you'll want to find some shortcuts. Okay. So what are we going to do with these constraints? So we're going to focus on our constraints, and what we're going to do is we're going to graph them all on one graph. Whoa, that's like way back in 1.1 stuff. I know, right? So to solve an optimization problem, I guess one is identify your objective function. So find the objective function. And you're going to want to keep these two separate, right? Your list of constraints is usually more than one thing, right? But the objective function is just going to be one linear function. And we're going to keep it separate. Okay? So then find the constraints. These will be linear functions or inequalities. Okay. Then graph all the constraints on one graph. I'm going to, oh, now it's letting me do it. Oh. We already started 3.1, but I want to do my own thing first. So, graph all the constraints. So notice how it's just the constraints, not the objective function. I'm going to keep that kind of parking lot that for a long time. So graph all the constraints on the same graph. What that's going to look like is usually something like this. If I have X and Y, let's say X is, I don't know, how much fabric I have. And let's say Y is how much time I have to spend on, I don't know, sewing something, sell it on Etsy or something. But I only have so much time. And I only have so much fabric, right? Can I have negative time? No, right? So generally, we're going to be restricted to positive Y values. Can I have negative fabric? No, be pretty hard, right? And so then we've got these first constraints where, and how we show it is that Y has to be greater than or equal to 0, right? And also X has to be greater than or equal to 0. Those are my first two constraints. And so now I'm restricted to that area in the graph. Everything else doesn't satisfy those two main constraints that we're going to start with. So then I'm having a hard time finding a relationship between these two, but maybe, I don't know, maybe the more time that I spend on a project, the less fabric I can buy. I don't know. I'm just making this stuff up. We've got curated examples coming up, but usually what happens is we have some constraints that maybe look like this. Right? So here we have two additional constraints, and I'm keeping it vague because I can't possibly make this stuff up. And so here, these are two additional constraints. So you're going to graph all those lines on the same graph. And let's say usually things have to be below this line. It can be the other way around, but for now, right, because I don't want to deal with the inequalities, we'll tackle that on its own. But let's say you've got it figured out and the inequalities say that, okay, you have to be below this line and you have to be below this line. And we'll use test points to figure out which region satisfies it. Okay. But what you're going to find is you'll use the inequalities to find the region where all the constraints are satisfied. To find the region where all the constraints are satisfied. This is called the feasible region or the feasibility region, I think they call it in this textbook, but this is called the feasible region, or sometimes we call it the feasible set. Feasible set, because it's going to give you a feasible set of XY coordinates, right, that satisfy all those constraints. Which means, okay, if I have to be below this line and below this line and to the right of this line and above this line, then my feasible region looks like this. The coolest part of it all is that, do you know how to find the intersection of these two lines? You do. How about the intersection of these two lines? You do. How about this point? Sure, why not? They're just intersections of lines. We spent a lot of time doing that. And so you can find all those intersections of the feasible set or the feasible region. Now, you're not going to believe this, but next time on, no, real cliffhanger, but the fundamental theorem of linear programming says, that sounds important, right? Says that the function that you're trying to optimize, right, the objective function, right, so now we pull it out of the parking lot, and the objective function will be optimized at one of these vertices, right? And so one of these intersections of the feasible region will give you the optimized result, right, for X and Y, right, the optimized coordinates. So how do I write that all down? How did I phrase this? Then find the X, Y coordinates of all the vertices. If I say vertices, the corners. Uh-oh. Like, don't think about it. A tickle in my throat from talking all day. All right. Oh, just talk through it, right? Find the XY coordinates of all the vertices. Just gonna let it pass. Of the feasible region. Oh. That's gonna take some work, right? These are going to be finding all the intersections. Find all the intersections. Of the feasible region. Notice how there are other intersections here, like this one, the y-intercept and the x-intercept of this one, but they're not in the feasible set, right? So all the constraints have to be satisfied. So you don't have to find those. Find all the intersections of the feasible region or the feasible set. Then what? Now you can bring back that objective function. Usually what we do is in a table, evaluate the objective function at each of those vertices. Evaluate the objective function at each of the vertices. The objective function will be optimized at one of those vertices, right? And if you're trying to maximize it, then you just pick the largest result, right? And that tells you what X and your Y should be to maximize it. Or if you're trying to minimize it, you pick the smallest result. And again, it just gives you the X, Y coordinates that make that happen. The objective function will, I'll underline the will be optimized at one of the vertices. I'm supposed to add if a solution exists, but let's just focus on where problems where solutions do exist, right? But that would be the follow-up. It's possible to have a situation where no solution exists. If you have unlimited resources, unlimited time, for example, but that's not going to happen. Okay. There's our roadmap. Okay. I'll bump this up here. So we'll start with maximization applications and then, well, not today. Next day we'll do minimization, but same procedure applies. Okay. It's giving you the outline. All right. And I didn't put any space between these examples, but we're gonna need a lot of space, so, and I'll upload these. Which I forgot. Okay. First example. Nikki holds 2 part-time jobs, job 1 and job 2. All right. She never wants to work more than a total of 12 hours a week. Sounds like a Jerry Springer. I never want to work more than 12 hours a week. Anyways, fair enough. So she never wants to work more than a total of 12 hours a week. That's a constraint, right? Okay, we're gonna have to work around that. She's determined that for every hour she works at job 1, she needs 2 hours of preparation time. Okay, I don't really understand her job, but whatever. And for every hour she works at job 2, she needs 1 hour of preparation time. She cannot spend more than 16 hours for preparation. She's working 12, she's prepping for 16. I don't know. I don't understand these jobs, but I think we can all agree that we have some constraints that we're trying to satisfy. If Nikki spells her name differently and also makes $40 an hour at job 1 and $30 an hour at job 2, how many hours should she work per week at each job to maximize her income? So we want to maximize her income. That's going to be our objective function, right? We want to maximize her income, making this our objective function. What's her total income? If we let X be the number of hours at job 1 and Y be the number of hours at job 2, right? And that takes practice, right? Here it's our first one, so I'm giving it to you, but let X be the number of hours at job 1 and Y be the number of hours at job 2. Then our objective function let's call it income. The income that she makes depends on how many hours she works at each job, right? And so she makes $40 an hour at job 1 and $30 an hour at job 2. That's a linear function, right? I've got an X and I've got a Y. I've got the income, which depends on X and Y, but that's going to be a constant. But now I've started this example. Okay, can we do it? We can, or at least we can start. We've got some constraints. The easy constraints are, well, she has to work some non-zero positive number of hours at each job. I guess in theory, she could work 0 hours at a job. And so our constraints, let's start with the easy ones. She can't work a negative number of hours, right? And so same as we saw before, X has to be greater than or equal to 0. And Y has to be greater than or equal to 0, which is nice because it puts us in that first quadrant of our graph, right? And we don't have to float around anywhere else. Now for the harder constraints. remembering that X is the number of hours at job 1 and Y is the number of hours at job 2. So the constraint is she doesn't want to work more than a total of 12 hours per week, right? So presumably it's per week. So our first constraint, real constraint, is going to be that X plus Y has to be less than or equal to 12. You can force it to be equal to 12, but she just doesn't want to work more than that, right? That's the restriction. So she can work less than 12 hours. She's not going to. Not if we have anything to say about it. But not if she wants to maximize her income. And so this is kind of the hours worked versus the preparation time. Every hour that she works at job 1, she needs 2 hours of preparation time, right? So then I'm gonna have 2 times X, because now my hours of prep is what I'm finding, right? So it depends on how many hours she works, but she has to multiply it by 2. And then for every hour that she works at job 2, she needs 1 hour of prep time, which puts us at 2X plus Y. And she cannot spend more than 16 hours on preparation. This that I potentially made seem really easy and breezy is really difficult, right? If you're reading this problem and kind of figuring it out, right, then you'll want to spend some time figuring out what your X and Y's are so that you can set up the rest of the constraints properly, right? But with some practice, you can do it. All right. Can I cheat? Can I use Desmos to draw it? I don't want to draw these. I'm going to draw just the straight lines. Okay? And I'll, just because I don't want to cheat too much. So X plus Y is equal to 12. Let me zoom in here. There. And we had 2X plus Y equal to 16. I know, tempting. I'm going to screenshot this. And bring it in. Oh, did it twice. So notice I did the equal sign, right? I just pretended this was a line, X plus Y is equal to 12 and 2X plus Y is equal to 16. Because Desmos will do the inequality if we let it, but I didn't want to do that. Can do it. The red is the 2X plus Y is equal to 16 and X plus Y is equal to 12 is the black line. I'll label those here. X plus Y is equal to 12 and 2X plus Y is equal to 16. To figure out if a value satisfies the inequality, right? Because X plus Y has to be less than or equal to 12, right? So on this line, it's equal to 12, right? But if it wants to be, if we want it to be less than or equal to 12, then if you're comfortable with saying that, okay, then that has to be this region below, that's cool. But what's another way you could test it? We also said that we're restricted to this region. Just kind of up from here. It's another way you could test it. Well, we could pick a point. We call them a test point. Let's see here. If this is 20, then I've got 1, 2, 3, 4 blocks. So each must be 5. And if I pick a point, a test point, when x is 1, that's here, and y is 5, right? What I can do, right, because that's in a region kind of below each of these lines, kind of 2 birds, 1 stone type of situation. Then check the inequality at the test point. And it can be any point in a region that you want to test. I picked 1, 5, but the goal is to say, okay, if x plus y at x equals 1 and y equals 5, that's going to be 1 plus 5, which is 6, which is less than or equal to 12, which tells me that that is in the region that I want, right? And not the region above, right? So if it's not in the region that you want, then it's the opposite region. And you can do the same thing for the 2x plus y. If x is 1, 2 times 1 plus y, which is 5, is 7, which is still less than or equal to 16. And that's why it's satisfied. So I like to put little arrows here. Okay. What's your next step that you're going to do on your own? And then we'll do it for a review. We'll pick up here on Thursday. But you're going to try to do it, right? Even with my brief instructions. Next step, you have to find the vertices, right? And so, oops, I want to boop, boop, boop. So your feasible region is up to here. There. And it's this region here. Next thing you need to do is find the vertices, right? Find the intersections of those lines. Some of them are easy, some of them are hard. Maybe not hard, but more fun. And we'll start there on Thursday. If you have any questions, let me know. Otherwise, you did great. I'll see you on Thursday.